Professor Sridhar Santhanam, who's the professor and chair of mechanical at Villanova University. Professor Santhanam received his doctorate from Arizona State, and he's been, I think since then, he's been on the faculty of mechanical engineering at Villanova. He's very active in working in the areas of modeling, processing, and high temperature materials, and structural health monitoring using ultrasonic methods, fatigue and fracture, and has worked on a number of projects with ONR, Air Force, NASA, and the National Science Foundation. So it's a great pleasure to have him with us. Thank you for agreeing to tell us about your work, and I'll invite you to start your seminar on monitoring and modeling for aerospace structural integrity.
Thank you, Professor Jairam. Can you hear me clearly?
Yes, yes.
And I assume you can see the slides on the screen?
Yep.
Okay, fantastic. Thank you. Thank you for the introduction. I also want to thank Professor Jairam and Professor Raghu Prakash and the Indian Structural Integrity of Structure Society for giving me this opportunity. It's a great honor and pleasure to present. I really appreciate you're joining this talk on a Saturday evening. I realize how valuable time is for everybody, and appreciate your joining this talk. And hopefully it'll be worth your while for the next 30 to 40 minutes of my presentation. As Professor Jairam said, I'm at the Mechanical Engineering Department at Villanova University. It's for those of you who are not familiar with the school, it's a private university situated just outside Philadelphia. The Philadelphia region has so many universities, such as, for example, University of Pennsylvania, Drexel University, and Temple, and Lehigh University is not that far away. So there's a cluster of schools around here. And Villanova occupies a certain niche. It's a private school, and strong undergraduate engineering program, and also very strong graduate program. A lot of PhD research going on over here. And I do have a couple of slides at the very end of the talk about to try to make a little pitch about my department and the university. So I'll save that for later. So my talk is going to be about monitoring and modeling for the integrity of aerospace structures. So there's a couple of different elements that my primary focus is going to be on the structural health monitoring side. And then towards the end, I'll talk a little bit about some of the work we've done on fatigue spectrum editing. So I'm just going to switch over to the next slide. Structural health monitoring, and that's going to be the focus of the first part of the talk. And some of the topics we will discover are things like, for instance, the different ways of doing structural health monitoring, many different what I call modalities. And but a lot of the work that we have done over here is focused on one particular modality, which is the use of ultrasonic waves or stress waves or guided waves in structures to look for defects, because that's essentially what structural health monitoring is all about, is to identify defects in structures so that you can prevent catastrophic failures, such as the one that you're seeing on the picture on the top right. That was a United Airlines flight, and you can see that the engine cover has blown away, revealing the engine directly. And this happened during mid-flight, and thankfully that particular aircraft landed safely. But those are the kinds of things that you want to see if you can identify early enough and thereby take preventive measures before anything really bad happens. There's many different ways of doing structural health monitoring, as I said, and guided waves or using ultrasonic waves is one way to do it. And then even there's specializations in terms of how you identify the defects. And so we're going to look at one particular way that we've focused on, which is the use of an idea called compressive sensing, which gained popularity primarily in communications first, electronic communications, and now it's being used very widely. And then the second part of my talk will focus on fatigue testing, and you can see a fatigue failure in a shaft at the bottom right. And well, how do you prevent such failures? Well, a lot of testing, obviously, in the lab, and especially in the aircraft aerospace business, you have to do lots of testing And so there are ways in which they do it, and they're pretty long drawn out, very time consuming and expensive. And well, can you fast forward that and make it shorter and cheaper? So again, motivation for structural health monitoring, many disasters, and here's just a few. There was a very infamous Aloha Airlines flight. This was way back many, many years ago, 1988. And you can see a portion of the fuselage just tore off from the plane. And what you're seeing in the picture on the top left is actually when the plane had just landed. As you can see, the passengers still in their seats, strapped to their with their seatbelts on, and these were the survivors. There was only one lone casualty. She was a stewardess, and she was standing somewhere in the middle of the plane, and where the cover or the fuselage blew off. She unfortunately, fell off the plane and was never found. Another example is, and this was not as catastrophic, but nevertheless pretty scary, which is C-130A Hercules air tanker crash. And you're seeing a picture of a C-130A plane, not the one that actually crashed, on the bottom left. Well, anyway, one of these planes was doing firefighting in somewhere in California, and both wings essentially broke away and in the mid-flight. And so basically it was just the fuselage of the plane that was left, and obviously it crashed and killed everybody on board. There were 3 people who died, and it was traced back to a flaw at one of the some of the stringers and the attachment points, and there was fatigue damage that was found. And so clearly that's something that we need to identify early enough to prevent such catastrophic failures. And of course, in 2007, there was a infamous, again, bridge failure across the Mississippi River in Minneapolis. And it was traced down to a gusset plate that joined various truss elements together. And it was a bad design, but even that could have been spotted in terms of, the failure sort of initiating early on and identifying it and making sure it doesn't happen, or taking corrective measures to prevent the failure. So yeah, whether it's planes or bridges or large structures, you want to be able to monitor these structures and just like the human body, identify potentially devastating defects early on so that you can take corrective measures. So structural health monitoring falls within a broader framework of what's called diagnosis and prognosis. So we know that structural failure initiates at flaws. These could be pre-existing flaws or flaws that arise later, and those, of course, you would characterize as damage. Say, for instance, a worker drops a tool on the surface of the wing of a plane, and that could leave a little dent, or perhaps a bird strike causes a dent, and which in turn initiates damage, which can grow with time and eventually cause failure. So diagnosis, there's 3 aspects to it. You have to first identify if there is a damage or not. And this could be at a global level or a local level. Global level in the sense that you sense that there's damage in the structure, you just don't know where it is. And at the local level, obviously, you sense that there's damage and you kind of know where it is. So that's identification. And localization is zooming into the specific location where the flaw or the defect is. And so that's just as important as identification. And then finally, classification, where you say, well, this particular flaw is of this type. It's a dent, it's a hole, it's a crack. And if it's a crack, is it a crack through the thickness of the structure, or is it between 2 bonded layers of the structure? There's a lot of composite materials being used in planes these days, and those are laminated. Some of them are laminated composites, and so there could be interlaminar cracks, and you want to classify them as well. And once you've done the diagnosis and you identified what the flaw is and where they are, then you have to do what's called prognosis. Not every flaw needs to be corrected or fixed right away. You can live with it, as we tend to do as human beings, right? You have issues with your physical body, and some things you can just live with, and some you have to fix. So that kind of assessment has to be done. and that's part of prognosis. And then obviously with aerospace structures, or for that matter, any structure, you want to make a prediction about the lifetime. And of course, there's a lot of modeling and theory that's available to do those predictions. And therefore you can forecast into the future. So where structural health monitoring lies is in the diagnostic side of things, right? It's not for prognosis, it's primarily for diagnosis. So again, structural health monitoring, or SHM for short, is a diagnostic tool. And how do we do this? Well, you want to do this in a way that you are continuously monitoring a structure. A lot of the approaches to aircraft structural monitoring has been one where you let the plane fly for a certain number of flights, and then you pull it out for inspection every now and then put it back into service. So obviously there's a fair amount of downtime associated with this sort of periodic maintenance approaches. Instead, what you probably want to do is transition to what's called condition-based maintenance, where you monitor the structure continuously, identify what its condition is. If it's good, keep flying. And if it's not, well, pull it out of service and fix it. So you have to mount sensors on your structure, and they have to exist on the structure. And this has to be done in a very unobtrusive way so that it doesn't interfere with the structural performance. And then the measurements have to be acquired from the sensors. And once you acquire the measurements, then you have to probe those measurements, analyze them to see if you can identify whether damage is present in those signals. So sometimes the presence of damage can cause a significant change in the measurements you're making with your sensors. And if you can identify that, then that's your ticket to trying to figure out whether there's damage or not. That's identification. Two, or B, where the damage is, that's localization. And then finally, what kind of damage is it? And is it bad? So that's classification. So again, structural health monitoring, many ways of doing it. This is what I'm showing on this slide is just a small selection of the different ways in which structural health monitoring is done. Vibration monitoring, for instance, has been around for a long time, and this has been very, very successful especially with rotordynamics, when you got shafts that are spinning with gears on them, or discs, or flywheels, etc. Vibration monitoring has been very successful at monitoring the health of those kinds of structures. So if you can identify the frequencies at which the structure is vibrating, and if there's a change in those frequencies or the amplitude, that's a clear sign that there's some issue with the structure. So that's a very popular way of doing it. Acoustic emission is another passive way of doing it. And I'll explain what passive versus active is in a short while. But basically, in acoustic emission, you mount sensors in your structure, and these just listen to the structure. And so whenever there's a damaging event that happens, typically, like for instance, a crack forms, then there's a release of strain energy in the structure, which is picked up as effectively sound propagating through the structure. And your sensors, if they pick that up, and if you can identify the severity of that sound, you can perhaps correlate that with either the location of the defect or the size of the defect. A third way of doing it is to put strain gauges on a structure, and you have a nice little picture of a strain gauge over there. And so that can monitor the amount of load that the structure is sensing, and or the strain that the structure is sensing. And again, if a defect forms in the vicinity of the strain gauge, then the strain reading is going to increase. And so that's another way to detect defects. So these are all passive methods where you just have these sensors sitting on the structure, and they don't do anything by themselves other than listen to the structure. And whenever something bad happens, then that the sensors pick that up. An active approach would involve periodically interrogating the structure with some signals. So you send a signal into the structure, and you look for any changes in the structure, and hopefully the signals are able to interact with the changes that you see in the structure that happen in the structure, and then get that information back to you through again the sensors. So that's what's called an active way of doing it. So this is done several different ways, and one popular emerging way of doing it is by the use of what's called guided waves. And so these are just stress waves that propagate through the structure, not unlike waves that propagate on the surface of water or in the ocean. So you have waves that propagate through all kinds of media, whether it's air or water or liquid, and solids, obviously, as well. And so there's a variety of different waves that propagate through structures, and one particular kind of wave is what's called a guided wave. So in the next 1 or 2 slides, we'll go over the concept of a guided wave and how you can exploit them to do structural health monitoring. By the way, if there, I assume if there are any questions, I can address them at the end. So, or if
yeah, we've asked people to type them in the chat box, and we can take them at the end.
Okay, thank you very much. Appreciate it. So waves in again, we're focusing on solids because most structures are made, all structures are made of solids. Couple of different kinds of waves. Bulk waves are waves that propagate through a large solid. For example, the Earth is one large solid, and there are bulk waves that propagate through it. So waves can propagate from one location to another location and through the volume of the Earth, and so that's an example of a bulk wave. And again, they come in different forms. There are what are called longitudinal waves or pressure waves. And then there are what are called transverse waves or shear waves. And it simply has to do with the nature of motion between the particles in a solid. In a longitudinal wave, the particles of a solid come together and go apart, come together and go apart. Whereas in a transverse or shear wave, one particle slides past another and then comes right back in the opposite direction. So that's a shear wave. Now, not all solids are large in terms of their all their dimensions, like Earth, for example. Many of them tend to be large in 2 dimensions, but thin in a 3rd dimension. For example, a classic example is a plate, or for that matter, any panel on the fuselage of a plane, for example, is basically a plate, a curved plate, or a shell, as you would call it. So these are thin structures in one direction, and large in other 2 directions. So that would be an example of a structure that is not infinite in all dimensions. And in such structures, it is found that you get a different kind of wave that forms. It's what's called a guided wave, and it's called guided because the wave that forms in the structure is guided by the finite thickness of the structure, and so it's forced to travel in only 2 dimensions as opposed to traveling in 3 dimensions, which is what a bulk wave does. And so it's guided by the what are called the surfaces of the solid. And so there's some special waves there. And again, this is a fairly old topic. It's been investigated for more than 100 years. Rayleigh, for instance, way back in 1917, formulated the concept of what's called a Rayleigh wave. And again, a lot of this work was done in the context of earthquakes. Geologists studied these waves. So Rayleigh waves is a classic earthquake type of wave. If you get a disturbance that happens in some part of the Earth, that quickly travels to the surface of the Earth and then propagates from there to another location. And that's a good example of a Rayleigh wave. Stoneleigh waves, again, are waves that propagate at the interface between 2 large plates that are bonded together. And then there's a whole bunch of others, including at the bottom, what's called a Lamb wave, which is, again, going to be the focus of the attention in this particular presentation, because we're going to exploit these Lamb waves to do our structural health monitoring. So what are Lamb waves? Well, the picture on top here kind of shows that. You have what's called a transducer, something that, or an actuator, something that initiates a wave. And that wave is initiated by a specific device, which is sitting on top of a plate. And if the coupling is good between the device and the plate, then the wave that is generated by the device is transmitted into the plate. And then after a lot of bouncing around, eventually, you get the formation of what's called a guided wave that propagates along the direction of the plate perpendicular to its thickness, right? And could travel in any direction within the plane of the plate. These days, a lot of these waves, can be triggered easily with some very simple transducers or actuators. These are just thin discs of a ceramic. Popular ceramic that's used is lead zirconate titanate, PZT. And you just glue them onto the surface of the plate and excite them with a voltage. And that in turn generates a wave that propagates into the structure. So those are the PZT transducers. And the nice thing about these guided waves is they travel long distances in the plate without significant attenuation. So that way, if you have a few judiciously placed transducers in your plate, you can cover a large area of the plate or interrogate a large area of the plate to see if there are defects in the plate. Another nice thing about these waves is, is that they're very sensitive to defects. So if there's a defect there, then the wave will interact with it. And therefore, once the interaction is done, then the wave that moves on is now contains information that's related to the defect. And so you can exploit that to do structural health monitoring. Some drawbacks, if you will, for these waves are that they possess multiple modes. So if you have a transducer over here and it instigates a wave, it turns out that what comes out is more than just one wave. There's multiple waves that come out. Some of them have this special property called symmetry. So they're called symmetric waves. And some have a special property called anti-symmetry, which is what's called an anti-symmetric wave. So there's multiple waves that come out, or multiple modes. And so that means you have a profusion of waves coming out and hitting your defect, if there's a defect there, and then which then gets picked up by sensing transducers. And so there's a lot of information coming at you, and sometimes it's all muddled together. And so it makes the task of trying to figure out what's happening that much harder. So that's a drawback. But as I'll show in a little while, we can actually exploit the presence of multiple modes and gather enough information that allows you to locate these defects. Another issue with these waves is that the speed depends on frequency, and transducers such as these, when they initiate a wave, typically they initiate a wave. We try to initiate them at a specific frequency, but invariably you get a range of frequencies that are triggered, and each frequency travels at a different speeds, and so consequently you might send out a nice tight wave initially, but because of the multiple frequencies in the wave, it spreads out, and suddenly what was a nice tight wave or a pulse is now a very wide pulse as it hits a defect and then arrives at your receiving transducer. And consequently, again, your information is spread out over a long period of time and overlaps with other incoming waves, thereby muddling the picture even more. And then further complications, if you have a finite size plate, then a wave that's initiated by a transducer will go out, hit the defect, and then might go hit the boundary of the plate, and then reflect back. And now you have to deal with the reflections of the boundaries of the plate too, which can, again, create a lot of confusion in your received signal. And so that's an issue too. But again, we're going to show here that we can exploit that, the fact that you have multiple reflections, and you can take advantage of those reflections to identify defects. This is just a quick illustration of this concept of wave speed, which is shown on the vertical axis, being a function of the frequency of the wave. And again, there's all the different modes that we talked about, and so that's why you got multiple graphs over here. I don't want to touch upon this too much, but basically it illustrates the concept of multiple modes and the concept of what's called frequency dependence of the wave speed, which is also known as dispersion. So here's a overall concept for a guided wave-based structural health monitoring system. So you got a plane, and obviously you want to monitor the critical structures in the plane. So, for instance, the wing, and you mount sensors on the wing. What would the sensors be for guided waves? There'd be these these thin discs of ceramic. I mentioned lead zirconate titanate, that's PZT. So you put in an array of these transducers. Here in this picture, I'm showing 4 transducers. Those dark circles are the transducers. And so again, as a designer of the system, you have to figure out how many transducers you want to put, where do you want to put them, where are the critical locations, how can you best identify where defects will arise, and so on. That's a separate issue entirely. So anyway, you have these transducers, and each one of them can initiate a wave, a guided wave, and can also receive a guided wave. So they function both as transmitters and receivers. And then you perhaps have defects inside in the region of interest. The ROI, or region of interest, is a phrase that I'll be using quite a bit over the next few minutes. So you could have holes that maybe they're pre-existing holes, or maybe there are holes that arise because of a bird strike or whatever, or cracks. So any kind of defect that's over here. And so these transducers are periodically excited, and the signals are picked up. And then typical signal looks like this. You have incident wave, and then reflections from the defects, and then unwanted reflections from the edges of the plate. All that is mixed together, and somehow you got to take that information and decipher it. Well, with this sort of scenario, you would have multiple transmitter-receiver combinations. So, for instance, you could transmit from 1 and receive at 2, receive at 3, receive at 4. So you have 3 signals that are coming through. Similarly, you can transmit from 2 and collect at 1, 3, and 4, and again, you have 3 more. So you have multiple combinations of transmitter receivers, each one of them giving you a signal. And so you have a lot of information coming. And so you collect all that information, and from that, you figure out, well, it looks like I have a defect at a certain location, and so on. So that's the analysis part of it. And obviously, all of this is going to require some hardware, and so you're going to need to have a way of exciting these transducers and also receiving the information from them. So a typical data acquisition system would be needed. And that would be on board somewhere on the plane, obviously. If I could go back one slide, the key here is to take these signals that are coming from the receivers and converting that into information into, here's where my defect is, and here's what kind of defect it is. So that's called imaging. You get the information, and then you figure out where the defects are. Right? So you image the defects. So imaging, as it turns out, has been a very well explored topic. Lots of different ways of doing it. There's some classic ways of doing it, what's called delay and sum beamforming. By the way, this imaging idea is not unique to structural health monitoring. It's used all over the place. A simple case like, for instance, a plane flying and keeping track of where it is, radar. You have multiple transmitters and receivers that are used for determining the location of a plane and how fast it's flying, and that relies on the same concept of imaging. You get the signals, radar signals, and from that you have to image where the plane is in space. So anyway, there's time of flight approaches, there's time reversal. Tomography is commonly used. Tomography is, again, very commonly used in medical imaging, for example, ultrasonic medical imaging, or for that matter, X-ray tomography. CT scans use that idea. So imaging cuts across lots of different disciplines, and we just exploit some of the ideas that are there. The particular topic that we focused on was the use of something called sparse reconstruction, which is something that has come about over the last, I would say, 10 to 15 years. Again, it was used primarily in the communications area. Radar, for example, that's where it was first introduced. If you approach it from the fundamental point of view, it's a very mathematical topic. A lot of research done by mathematicians and statisticians. But it has also permeated into engineering a lot, and today it's commonly used. Of course, we used it about 4 or 5 years ago. A lot of this work was done about 4 or 5 years ago, and today it's a very widely used tool. So I'll just go briefly what the sparse reconstruction method is for imaging. And There are a lot of technical details to it. I'll just try to stay high above and cover the broad foundations as opposed to getting into the weeds and getting into the details. So again, it's a little mathematical. So the next one or two slides might appear to be focused on the math, but at its heart, it's not that difficult a concept. Sparse reconstruction, from a mathematical perspective, it relies on solving a set of simultaneous linear algebra equations, things that we did in high school or middle school. So you have some unknowns, maybe there's 3 or 4 or 5, and then you have what's called the coefficient matrix, and then this is the what we call the solution vector. So standard y is equal to m times x, right? Except that it's in multiple, you have multiple x's and multiple y's. And usually the number of unknowns is equal to the number of equations. So m is the number of equations and n is the number of unknowns. And typically m equals n for a well-determined system. And that's solvable. What you do is you take your coefficient matrix and invert it and multiply it with your left-hand side vector and solve for the unknowns. But in imaging, as it turns out, and the way we're going to construct it right now, this n is much larger than m. So you have very few equations and lots of unknowns. And of course, we know that's very difficult to solve, right? That's what we call an underdetermined system of equations. Not enough information, too many unknowns, and that's always a problem. Well, how do you deal with this? Well, it turns out that if your problem is such that even though you have lots of unknowns, but only some of them are non-zero, most of them are zero. It's just that you don't know which ones are non-zero and which ones are zero, but a majority of the unknowns are zero and just a few that are non-zero. If that is the situation, then it turns out that the equations can be salvaged and you can actually get a solution. Okay, so this is what's called a sparse problem. Sparse in the sense that very few of the unknowns are not zero. Most of them are zeros. Right? So that's kind of what's stated over here. So sparse reconstruction relies on the solution vector, which is the unknown vector, unknown x's, being very sparse. And there's a technique called orthogonal match pursuit, which I won't get into details of how you then find those non-zero unknowns in your problem. So how do we take this mathematical methodology, sparse reconstruction, applied to our specific guided wave imaging problem? So let's suppose I have a plate over here, and my defect, I believe, lies somewhere in this grid. And one of the cells in this grid is, or maybe more than one cell in the grid is where my defects are. My strategy would be, well, let me put a few transducers. So these little triangles that you see here are the transducers. There's 5 of them in this particular case. And they're distributed around a circle that surrounds the grid in which the defect is supposedly located. And so one thing I do know is that typically the number of defects tends to be very small. Hopefully that's the case. Otherwise, your structure is no good. So your structure is healthy, but occasionally a defect can arise. And so when that does happen, there's very few of them. So only 1, maybe 2, maybe 3 of these cells is populated with a defect. The other cells have no defects. So a defect could be in, for instance, the top left cell over there, and that's it. So every other cell, there's no defect. So if you could say that if a defect is present in a cell, then you assign the number 1 to that cell, and a defect is not present in the cell, you assign a number 0. So then you would have what's called a very sparse grid. So only one of the cells has a 1, and the other cells are all 0. So that essentially would then function as my x unknown vector. Lots of zeros and just 1 or 2 1s, and I just don't know where they are, and I'm trying to find them. Okay, and then so that is my x vector. Now, what is my z vector, which is the left-hand side over here? Well, that's the signal that I'm getting when I activate one of these transducers and let it send a guided wave through this region. and let it interact with whatever is here, defects, etc., and then arrive at my receiving transducers. There's 4 of them. And I can activate each transducer in turn and receive at all other 4 transducers. And so basically I have 5 times 4, 20 signals that I can get effectively. And that will, so those 20 signals constitute my Z vector. And then this middle matrix that connects the received signal to the potential of defects being in my structure, that matrix is given a special name. It's called what's called a dictionary matrix. And that dictionary matrix can be computed using modeling. So guided wave, how they propagate through a structure, how they interact with defects is a well-studied topic. And we have pretty good idea of how these waves propagate through a known structure. And so we can figure out precisely what that dictionary matrix is from modeling. So this matrix is determined using modeling. This is your unknown defect location vector. You're trying to find it. And this is your collected signal. And this X vector is very sparse, very few zeros in it, very few defects in your structure. So then you can attack it with this orthogonal match pursuit algorithm and solve for the locations of the defects. So that's fundamentally, in a broad sense, how we use sparse reconstruction, adapt sparse reconstruction, which is a mathematical concept, and apply it to this particular application where there's imaging using guided waves. All right, so now I'm just going to run through a few different ways in which we've applied sparse reconstruction to in guided wave imaging. In this particular one, we're going to take a look at how we use, I mentioned how when you instigate a Lamb wave in a plate using transducers, you get multiple modes. It's not just one wave that comes out, it's multiple different waves that come out, each traveling at different speeds, each interacting with your defect, each arriving at your receiving transducer. And therefore, you've got tons of information coming. And sometimes that can be very confusing and very difficult to deal with. If you've got tons of information coming in, it's all overlapped. It makes it difficult to analyze this received signals. But if you're careful in how you do it, you can actually exploit this profusion information that's coming and take advantage of it and to localize and identify defects better than if you just used one specific mode or one specific wave. So that's kind of the focus of the next few slides. Why would you want to do this? Well, it turns out that when I talk about the different modes, some modes are what are called symmetric modes, where the motion of the particles of the solid as the wave propagates to a structure can be seen as a symmetric motion, as opposed to anti-symmetric modes. So if you've got an S symmetric mode, I label that as an S mode. And if you have an anti-symmetric mode of wave propagating to a structure, I call that an anti-symmetric mode. Certain defects will interact with really well with symmetric modes, and certain other defects will interact well with anti-symmetric modes. So if you have both kinds of defects present in your structure, and if you only interrogate it with one particular mode, then you're losing out information about the other kinds of defects. On the other hand, if you exploit both modes simultaneously, you have the potential to identify defects that can be identified only with one mode or the other mode. So that's the motivation for doing what I call multi-mode imaging. Again, this slide kind of illustrates the same thing. You might have defects that are symmetric. So you could have a crack coming in from the top and a crack emanating from the bottom of the plate. And so that's called a symmetric defect. And then you could also have, by the way, the other way to look at this is the defect is in the middle over here, as opposed to being at the top surface or the bottom surface. So that might be a better illustration of a symmetric defect. And an asymmetric defect would be one which only emerges or goes into the plate from one side of the one surface of the plate, the top surface in this case. So again, symmetric waves will interact well with symmetric defects, and anti-symmetric waves will interact well with anti-symmetric or asymmetric defects. And that's the concept we want to exploit here. It turns out that when you have a transmitter which emits both antisymmetric and symmetric waves, it can produce multiple other modes, and so a lot of information coming to your receiver. And so you can build dictionary matrices for each of those combinations. And the X vector, of course, is your unknown vector. And this, of course, is the received signals from your transducers. And this is just an experimental arrangement here. So again, quickly, if you use just if you have two defects in your structure, and the open circles here represent the locations of the defects, the triangles here represent the location of the transducers, and any of these solids, colored small rectangles that you see, or squares that you see here, represent our predictions of where the defects are based on sparse reconstruction. And so you can see over here, if you used only the A0 mode for sensing these defects, then you can identify one defect well, but not the other one. And if you use the S0 only, then you can identify one defect, but not the other one. You can see where the guesses are way off from where the defect is. And on the other hand, if you simultaneously use both modes, what we call the multimodal imaging, you can identify where the defects are. Both defects are fairly precisely over here. So that's the advantage of multimodal. And this, by the way, is experimental study and not a theoretical one. I talked about the use of multi-path, which is, if you've got a plate with finite boundaries, and you get a lot of reflections from the boundaries, and so that can confuse the picture. But you can exploit that too. And so this next couple of slides will show you the concept of multi-path imaging. And so in this case, again, what you're looking at is here's a transmitter, here's a receiver, here's a defect, and these two edges, one vertical, one horizontal, represent the edges of the plate. And so you could have a wave starting from your transmitter, hitting your defect, and then coming to your receiver. The same wave that emanates from your transmitter could go hit the wall, bounce back and go hit your defect, and then go hit arrive at your receiver. So there's multiple pathways for a wave to start here, the transmitter, and arrive at the receiver, interact with the defect, and interact with the edges of the wall. So how do you exploit all that information? Well, again, for each path, you construct a dictionary matrix. And for each path, you have a defect unknown vector. Of course, these X0, X1, X2, X3 must all be identical because the defects are always at the same spot. They don't change just because the path of the wave changes. So you exploit that idea. And again, these are some details related to the experiment, but let me quickly run through the next couple of slides to show you some of the results. Here's a case where I've got just one defect in my plate. It is situated at this open circle. Again, this is experimental results. These triangles, as before, are the 4 transducers that I have, and this represents an edge of a plate. And if I use just one path, the direct path, to try to identify where the defect is for this particular situation, the sparse reconstruction model says, well, the defect is over here, right at the edge of the plate, and it's nowhere near where the actual defect is. So the single path method just fails. But on the other hand, if I exploit the fact that there's multiple pathways for a wave to propagate from a transmitter, arrive at the defect, bounce off the wall, and then come to another receiver, if I exploit all those different paths, then that's called a multi-path approach. And now I can precisely identify where the defect is. Now, the challenge over here was that the defect is very close to the location of one of the transducers. And also there's the edge of the plate very close by. And so multi-path allows us to identify where the defect is pretty well. I think I jumped too fast. Just one more slide here. This time we've got 2 defects, 2 circles here, and you want to locate where they are. Single path model, you locate one of them, but not the other. You notice that the prediction for the second one is over there. That's bad. On the other hand, if you use multi-path, you can spot where the 2 defects are fairly precisely. So it's a very effective method using sparse reconstruction in conjunction with multipath modeling. You can do the same thing with not just flat plates, but now pipes. So again, structural health monitoring of pipes is a very big application, especially for the oil and gas industry. You want to spot those defects pretty quickly, especially in the field where corrosion is a major problem and slowly eats into the wall of your pipe. You want to spot those defects quickly, as and when they rise up in your structure. So we've done the same multi-path modeling here. This time the paths are a little more complicated. They tend to be helical because you don't have a pathway straight from one location to another location in a plane. You're going to go around the surface of the tube, the pipe, as you develop your paths for the waves. So, but fundamentally, it's same idea. And so you get all kinds of pipes, and again, the paths are all helical. Right-handed helix, left-handed helix. So the R stands for right-handed helix, L stands for left-handed helix. You can take the cylindrical surface and unwrap it and make it rectangular or flat. And so then you can take the ideas that you develop for a flat plate, and apply it to a cylindrical pipe as well. So, and the details you can find it in one of the papers that we published. I'll skip that these details, and just shows you the experimental setup. So if you have a defect that's located over here, and you just do one single path, and your predictions are all over the place, but nowhere near where the defect is. But if you use multipath or the multipath modeling, then, or in this case 4 paths, you can identify where that defect is pretty well. Another example where the single path fails, that's your defect, but your predictions are everywhere else. And here's a case where there's your defect, and you identified where the defect is pretty well. Notice how you have 3 predictions over here. So that's the thing that sparse reconstruction allows you. I mean, a priori, you're not going to know how many defects you have in your structure. Now, we just happen to know how many defects we have because we put them in. But in practice, you're not going to know how many defects there are in your structure. There could be 1, there could be 2, there could be 3. And so in sparse reconstruction, what you do is you can decide how many defects you want to look for. And so you can say, well, I'm assuming there are 3 defects. Tell me where they could be. And so that's kind of what we've done here. Now you've got 2 defects in your structure, one located over here, one located there. And multipath, you can identify where both are pretty accurately. This time we put in holes, and once again, we're very successful at identifying where these holes are. These are 10 millimeter diameter holes. They're fairly big holes, yes, but you can spot where they are. And then even larger holes, you can spot them fairly clearly as well. I'll skip the next few slides. They deal with pipes where, not empty pipes, but pipes where you have fluid filled in them, in which case you have a different guided wave mode that's activated. It's called the quasi-Schultz mode, and it's very similar to the other modes that you see in pipes. So I won't get into the details. And I know I'm running short of time, so I'm just going to quickly run to the next topic and spend just about 3 or 4 minutes describing that, and then close out. So just to conclude this particular topic on structural health monitoring, it's a very viable diagnostic tool. It's being used in applications today, especially with pipes. There are commercial systems available that use guided wave imaging to identify where defects are in pipes. On the aerospace industry, though, it's a very conservative industry. They don't like quick changes. It has to be approved by lots of agencies before it can be used in practice. So it's not there yet. There's a lot of work being done, a lot in the labs, but it's not being used yet. So we still have a few more years to go before it'll be an approved diagnostic tool for aerospace structures. Anyway, we've shown that sparse reconstruction is a very viable imaging technique. And what would appear to be a problem with guided wave imaging, which is multiple modes and multiple paths, you can actually exploit them and take advantage of them to enhance the imaging. So that probably is the biggest contribution from the work that we've done. Very good. Professor Jaram, I guess I have another 5 minutes. I could stop here, or I could jump on the next topic.
Please go ahead. Go ahead.
Okay. So our next topic, and I'll keep it this one very brief, deals with fatigue testing. It is still related to structural health monitoring because obviously defects are caused by fatigue loading, and one of the ways of making sure that your structure is sound is doing a thorough test on it before you put it into service, or test on the components of the structure that you're going to put into service. And of course, in the case of aircraft, that means testing it with real fatigue loads that are seen in service. Every takeoff and landing, there's a lot of fatigue that happens, whether it be a commercial aircraft or a transport aircraft or a fighter jet aircraft. And so the aircraft industry is very, very sensitive to fatigue, and so they do extensive testing. And one of the ways in which they do this testing is by saying, well, let us collect fatigue load data that a typical plane sees over its lifetime, and then take that data, and basically that's a spectrum. You got large loads, small loads, large frequencies, small frequencies. It's an example of what's called variable amplitude loading, and you compile all this data, and then you give it to the folks that do the testing in the labs, and you tell them, well, this is the load pattern that I want you to apply on your components that you're testing in your labs, and check to see if your component can withstand these loads. And then we will take that component and put it onto our planes. So that's kind of the approach that the aircraft industry takes for fatigue testing. So there's all kinds of fatigue spectra that are available, publicly published. We'll talk about a couple of them shortly. The problem with this approach is that, and this slide kind of illustrates that, the problem with this is the testing times tend to be very lengthy. These spectra that are collected are for 500 flights, 600 flights, 1,000 flights. And so if you were to implement these fatigue spectra for testing of components in your lab, it's going to take days, maybe weeks, maybe even months before you finish a test on a number of components, a statistically valid number of components. And the costs can be pretty high too, obviously. Long times, well, it leads to high costs. So how do you hasten up or speed up this testing without compromising the results? Lots of different approaches have been tried. People have tried, for example, let me go to the next slide. There we go. Accelerated testing, where you increase the frequency of the applied loads, or you just go with high amplitude loading. Stress test your structure with high amplitudes and somehow use that information to figure out how the structure would behave when there's low amplitude loading. Also, there's many loading cycles inside your spectrum which correspond to low amplitude loads, which usually don't cause a lot of damage. So you can throw them out. So these are some of the approaches people have taken. A lot of transform techniques have been used on these spectra, things like Fourier transforms and wavelet transforms, and the technique that we've used is wavelet transforms. Let me go back one slide and talk a little bit about these aircraft fatigue spectra. So some very popular spectra that I used. There's one called Falstaff. It stands for Fighter Aircraft Loading Standard for Fatigue. That's the expansion. And basically, it's been compiled over about 300 or 400 flights of a fighter aircraft, and there's 18,000 cycles. A cycle is basically an increase in load followed by a decrease in load. And so those 18,000 cycles are shown in this graph. And obviously, if you want to put 18,000 cycles inside a small rectangle, then it's going to look pretty crowded. And that's what you're seeing over here. So the cycles are along the x-axis, and the non-dimensionalized loading amplitude is shown on the y-axis. And so it's a very busy pattern. And you can see that the amplitude is changing dramatically as you go from left to right. So that's an example of variable amplitude loading. And so imagine taking this spectrum and giving it to somebody in the lab and saying, well, test your component with this loading pattern. Well, it's going to take a long time. And of course, it's testing is expensive because you're going to have to test lots of samples with the same spectrum. And then there's another one called TWIST. This one is used not for fighter aircraft, it's used for transport aircraft. And again, these are published spectra by the aircraft industry. And this one has about 400,000 cycles. So that's a lot more than the 18,000 that you see in Falstaff. So it's all crowded. And obviously, you have to expand it out to look at the details of any given cycle. But, in the interest of showing it all together, it's all pretty crowded over here. Other spectra exist, helix, felix, etc., but we'll primarily focus on Falstaff and TWIST. So here's the approach we're taking for what's called spectrum editing. Spectrum editing is taking the huge spectrum and then compressing it so that you have fewer cycles to deal with, and therefore your testing can be done quicker, and the costs are reduced. But simultaneously, if you're going to scrunch the spectrum down to a smaller portion, you want to make sure that you're not compromising anything. And so the compromise, if you do it poorly, then you compromise because the damage you introduce in your component when you've got a edited spectrum might be very different from the damage that you get if it was subject to the full spectrum. And so it's important to make sure that the damage that you get from an edited spectrum is about the same as the damage you get from a full spectrum. So if you enforce that condition, then your spectrum editing is successful. So this is our approach. If you've got a particular spectrum that you want to scrunch down, edit, then we implement something called a fast wavelet transform, and then once we transform or edited the spectrum, we calculate the damage. You can do it a couple of different ways, using something called a stress life model, or you could use crack propagation ideas. We've done both. And from that, you predict the life or the damage. And if the damage doesn't match up with that imposed by the full spectrum, then you go back and change your parameters of the fast wavelet transform. And then you optimize the choice of the fast wavelet transform parameters by doing the cyclic approach. And so we use a genetic algorithm for doing that optimization. These are some details related to the wavelet transform. I will not get into it. It's single slide doesn't do it justice, so I'll skip this. Fundamentally, you're removing the high frequency amplitudes and keeping the low frequency amplitudes, because it's been found that the low frequency amplitudes are the ones that are the most harmful for the structure. And so we retain those. And so that's the wavelet transform enables us to do that. And again, as I mentioned, you want to make sure that the full spectrum and the edited spectrum are equivalent, and you do that by making sure the damage is about the same. And we've used both the stress life model and a crack growth model. And all of this, you can do this within commercially available software that do fatigue crack growth, for example. And some details about the genetic algorithm. It's a very nice way of doing optimization. And again, there are software tools available that will help you do this. So just a quick result. This is the twist spectrum. The red region here, which starts from all the way from the left all the way to the right, is the full spectrum. That's the original signal. And then the black portion here is your compressed edited signal. So we've achieved a significant amount of compression by eliminating, again, the high frequency parts that don't cause much damage. And we made sure that the damage between the full spectrum and the edited spectrum is not different by more than 5%. So that was our constraint. And this kind of shows us some more results. We do what's called use a blocking technique. And so we developed an algorithm called block wave gen. And for the twist spectrum, we've found that depending on the size of the block, you can achieve various amounts of reduction. That's the dark line. And in terms of the damage difference, we want to keep it less than 5%. We find that we can keep it less than 5% for each of these different chosen block sizes. Again, a lot of the details can be found in one or two of our published papers on this topic, which I'm happy to share. So in terms of spectrum editing, we've been able to show that you can use wavelet transforms and genetic optimization to do editing. And the amount of damage is about the same, whether it's a full spectrum or the edited spectrum. And we've been able to identify or show that the key attributes of the original spectrum are retained in the edited spectrum. So that kind of concludes the technical portion of my talk. I just want to make a quick pitch for, if I may be allowed to do it, for the mechanical engineering department at my university. We have 4 major areas of research that we work on. I'm in the materials and manufacturing group. We have several faculty members there. We have a strong group that does autonomous system robotics, whether it be unmanned boats, unmanned drones, and then even little flying bees and so on. We've got a new faculty member, Rebecca McGill, who does work with something called the Robo-Bee that was developed at Harvard University. And then we have a very strong group doing thermal fluids on energy-based research, sustainable energy and alternative forms of new energy and so on. So it's a very active group of faculty. In terms of our PhD students, we've got 48 PhD students in the program, and we have a number of openings. If there are students in the audience, then we do offer a lot of research assistantships for PhD students in lots of these areas, and we are currently looking for students in each of these areas in the next few months. So if you're interested, please do get in touch with me, and I'd be happy to connect you with the appropriate faculty member who does research in that area. I think I've talked too long. I thank you very much, and I'm more than happy to answer questions. Thank you.
Thank you, Professor Sridhar, for the excellent talk. So I'm sure there are a number of questions from the audience. From what I see in the chat box, there are a couple of questions. One says, what is the typical cost? This is from Mahendra. What is the typical cost of setting up the experiment in terms of transducers, data acquisition system? Can it be done by the PI without any external funding? So would you like to answer that?
Sure. So the cost, obviously the test bed is not that expensive. These are just, depending on what you want to look at, whether it's plates, could be, of course, aluminum is used a lot in the aerospace business, so aluminum plates, and composites again are used, and those are not that expensive either. The transducers are very inexpensive. I mean, here, those PZT transducers, if you're looking at small discs, 5 millimeters in diameter, 10 millimeters in diameter, it's a few dollars per piece, $3 or $4. Of course, it adds up when you're using a lot of them, and some of them are fragile, and you could break them while in use. But that's not a big. I think the biggest cost is going to be the data acquisition. You need a function generator, and then you need an amplifier and so on. Those can be a little on the expensive side. I would say, again, I can only speak in US dollars, but $15,000 to $20,000. So that's an investment you have to make. But once you have that, then you can do so many different things with it. Those things can be used with all kinds of different transducers, not just the PZT ones, but also the handheld transducers, and then of course lots of different possibilities with structural health monitoring. So a lot of things become possible once you make that initial investment in so it's the hardware that's the expensive side, the data acquisition system.
Okay, thank you. I see that there is a raised hand from Vikram.
Yeah, I wanted to ask you the defects that you detect. you know that there is something there, but what else can you say about it in terms of the size or the shape or anything else?
That's a good question. So our focus has been primarily on localization, which is, okay, there's a defect there. Can I clearly identify where it is located? Now, what type of defect is it? Is it a crack or a dent or erosion, which is basically a loss of thickness in that region? That we are still working on that. That's a little bit harder, I think.
But I guess the point is that once you know roughly where it is, you can use other techniques to get more details of what's there, because you know where to look.
Yes, yeah. Though it'd be nice if you could also, if it's in an inaccessible area, and if it's going to be expensive for you to go and open it up, like for instance, an underground pipe. It'd be nice to know that this defect exists, and this is the strength of the defect, and this is the nature of the defect. So you can ignore it if you need to. So I think, yeah, I mean, you're right. Yeah, absolutely. If once you know where the location is, then you certainly would want to then use other techniques.
There are two questions from Sundar. One is on structural health monitoring. He's asking what sensors are currently in aviation service usage. Specifically, are acoustic emission or strain monitoring or electromechanical impedance sensors used on any of the passenger liners flying today? Is weight penalty an issue in implementing the online condition monitoring of airframes? This is the first question.
Great questions. Yeah. I don't know that any of these, at least not publicly disclosed, any of these methods are being used on a commercial airliner flying today. They might be being used, I think, in some of the on the defense side, maybe the fighter jets and so on. That those tend to be a little bit more classified, but I think that's what I mean. I know people at Boeing that work on the defense side of things that are using some of these tools in there, and most of it is in the form of guided waves as well as strain based sensors. So you can mount, and even some fiber optic systems are starting to being used, but those are again very delicate and so on. But yeah, so that I think that was the first question. Are they being used in commercial things? And the answer, from what I've seen in the publicly available information, no, they're not.
So the second part of the question is about the weight penalty as an issue in implementing online condition monitoring.
Absolutely. That's I think that that is definitely an issue.
No, please go ahead.
Weight penalty is definitely an issue, especially with certain techniques. I think, I mean, the guided wave method with the transducers themselves, there's not much of a penalty, but it's just you have to get the signals into the transducers and get them out, so that there's all the wiring issues and so on that you have to deal with, and that means putting them in, and so that certainly adds a little bit, and then the hardware, you have to put in the transmitters and the function generators and so on. So yes, that is a concern, and but if the benefit is there in terms of being able to identify defects and prevent catastrophic failures, I think the aerospace industry will go for it. But yeah, certain methods have a higher weight penalty than others.
On spectrum editing, he's asking, have you experimentally compared wavelet transform or GA technique with rainflow based editing that is currently the industry standard? After all, rainflow carries a fatigue or physical basis built around closed cycles.
Have we compared it?
with the
No,
rainflow-based editing?
So we did so in one of the approaches we did use rainflow counting. That's the one where we did stress life assessment, and so we took advantage of rainflow counting to figure out which cycles fall into which category, and then use that to predict the life or predict the damage rather. Have we compared the GA method with that? I don't think we've done that yet. No.
Okay. See, my own out of my own curiosity, I want to ask: supposing you have kind of condensed the spectrum to what you showed, like 25% is the what you call reconstituted twist or whatever it is.
Right.
Is it applicable for both metals and composites, or you have to do different analysis to get what is good for metals and what is good for composites?
A good question. Yeah, I think ours was very specific to a particular alloy. So we're doing it for, say, for instance, fatigue crack growth for a certain alloy, and so the DADN characteristics for that particular alloy, you have to use those numbers in your calculations. So so yes, it has to be specific to the material parameters that you're working with.
Does it also depend on the the sequence sensitivity?
Absolutely. I mean, fatigue crack growth, if you that's in variable amplitude loading, you have to take advantage of the models that we have, and so which we did, yes.
Okay, the reason why I'm asking is, see, we did long back, condensation of this Falstaff spectrum to a programmed Falstaff spectrum, and in that case, we retained the sequence of the major loads. There are some 18 major loads that we identified, and then we left them in their slots, so that the resultant spectrum still had the beach marks on the fracture surface, which was used to kind of identify the crack growth rate for 200 flights of Falstaff loading. But then recently I tried to kind of evaluate for the carbon fiber composite, and it so turned out that these are not comparable.
Yeah.
Right. So what I want to ask is, if supposing I did the spectrum reorganization based on your wavelet or GA, and figured out that this is the best combination for the metallic materials, would I get a conservative life if I use the same spectrum for composites or otherwise? I mean, the idea is that, if I do one spectrum reconstitution by any of these algorithms, and if supposing I understand that metals is going to be the conservative life, then I would probably use that with a kind of a pinch of salt for the composites,
right,
or vice versa. Right. So
yeah.
what is your answer for this?
I would say, instead of making predictions like that, I would just go back and do the because the costs are not too much in the modeling side. So I would go back and redo the whole GA-based optimization for the composite material, and then find out what the edited spectrum is for that, as opposed to, because the failure modes are going to be different for a composite, on the damage development modes are going to be different for a composite versus a aluminum metal, for example. So I would, and the crack growth DADN curves are different.
Yeah.
So rather than guessing about, or not, well, even educated guessing about, is it can I use the one that I developed for a metal for a composite? I would just go ahead and do the modeling and figure it out. And also, maybe I should ask you this question. So a lot of the Falstaff spectrum and twist spectrum have been developed have been obtained experimentally from metal planes.
Yeah.
And now you got all these, especially on the fighter jet side, you got a lot of composite materials being used.
Yeah.
Is the Falstaff spectrum still valid for a composite?
Well,
plane?
I would put it this way. I think the spectra for the twist or Falstaff, I think they were obtained based on the what do you call the flight data recorders or the G meters,
Right.
and they do not per se correspond to some specific component. But then when you want to use it for some particular location, you have to derive the the local spectrum from the global loading sequence.
Okay.
So I think that's
I'd
where
like to
it
add,
makes. Yeah.
Raghu, what
Yeah.
you said was absolutely right.
Mhm.
Professor Santhanam, you see the two load spectra in question, Falstaff and twist, both were obtained at mainly by the Dutch and Germans in Europe using flight data records. And if you look at twist, it reflects the thrust load spectrum, which is an atmospheric phenomenon. So it doesn't matter what material is involved. Whereas Falstaff is mainly, it reflects the maneuver related G loads on the airframe. That again doesn't depend on whether, on what material the structure is made of. So, but your concern is very valid, because you would have to be worried about what component of the spectrum affects damage in metals versus composites. And I think that's really the point that Raghu was making also.
No, in fact, I have got my student to look at it not just from the nonlinear damage mechanics. I also need to look at the residual strength models with respect to composites. You cannot do the spectrum condensation by just going with even with the damage accumulation models. You also have to take into account the residual strength. So it looks to be a little more complex than what is done for the metals. Anyway, I think we are running short of time. I think there are two more questions. I will just go through that. Is there a way to characterize a defect using sparse reconstruction?
I don't know if the sparse reconstruction that is the key. I think it's just do you have information in your signal that reflects the nature of the defect? So for example, if you've got a crack, and the crack will have a certain orientation, and so depending on where the transmitter and receiver are, you might or might not get a signal from that crack. And so just based on that, you could then figure out, okay, I have signals for these combinations of transmitters and receivers, but for these others, I don't see it. So there must be a crack, and its orientation must be like this, and that's why it's reflecting in certain directions and not in other directions. So I think that's where the information lies. And yes, you could obviously sparse reconstruction will work whether it's a crack or another kind of defect, but you need to probe additional things in your signal that allow you then to identify what the defect is. But
well,
yeah,
he seems to have followed it up with the one more point, namely characterize in the sense identify whether it's a porosity or crack or delamination.
Yeah, that's, have we done that? No, that's a very difficult thing. And again, it all depends on the sizes of the defects too. If the defects are small, then the signals are weak, and then there's noise and so on. So this is complicated. But can you differentiate between a delamination and a hole? I think that's where those multiple modes that I talked about would be helpful. Delamination is something that will affect only one particular mode and not the other. The asymmetric modes, for example, are the ones that are impacted or interact with delaminations, and the symmetric modes usually do not. So if you can probe with both those modes and you see response from the asymmetric mode but not from the symmetric mode, then that will kind of give you an idea that it's a delamination as opposed to another kind of defect. So yes, you can exploit the interaction between modes and defects to then figure out, is it this kind of defect or the other kind of defect. that's where I think we need to go with this work is to now look at, can you identify the classification part of the problem. We've done localization, identification, localization, but classification I think is the next part of the challenge.
Okay, there is one question from Nishant Singh from IIT Kanpur. What are the cost-effective SHM approaches that you will suggest for expendable launch vehicles? And he is very specific on expendable launch vehicles. So.
Yeah. I would say some sort of passive technique would be, well, if it's expendable. But no, I see what you're saying. I think some sort of passive technique would work. But again, there's the weight penalty that Dr. Sundar mentioned. That's always an issue with all these things, especially with if you're dealing with expendable kind of micro air vehicles and so on. But I would say a passive technique would be better than an active technique, and maybe just acoustic sensors or simple strain gauges.
Okay. Yeah, I mean, I think we are running short of time. So I think on behalf of all the attendees and from the organizer side, I'd like to thank Professor Sridhar Santhanam for having taken out his time out for delivering this webinar for the Indian Structural Integrity Society. We'll all thank him by a round of applause, and then thank you, Sridhar. And we do look forward to you joining us, if time permits, to the Structural Integrity Conference to be held in Hyderabad during December 14 to 16 at IIT Hyderabad. So this is the information for all others too. Yeah. So thank you very much.
Thank you.
Thank you for the opportunity. Really appreciate it. Thank you.